Hey guys, I want to do a video that goes through all of the multi-select multiple choice on the linear algebra sample term test and just go through why each of them are true and why they're false, since the solutions don't really have any justification. So let's get right into it. We've got z as some complex number, and we'll just take z as the form of a plus bj. And which of the following must be true? So we've got the real of the imaginary of z equals 0. So this one is quite straightforward. We've got the imaginary of z. We know that this is equal to b. So if we were to take the real of the imaginary of z, which is just b, which is, since b is a real number, we're taking the real of a real number, which is b. So b does not equal 0. Therefore, A must be false. Okay? So, second question. So we're given if z does not equal 0, then the inverse of z equals some formula here. So basically, let's just take the inverse of z and let's rationalize it to see if we can get that form. So we've got 1 over z, or 1 over a plus bj, and we just need to rationalize it. So we'll multiply the top and the bottom by the conjugate, and we get a minus bj over, and then we have a difference of squares here. So we've got a squared minus b squared j squared. So you'll remember that j squared is equal to -1. So the bottom will simplify to a squared plus b squared. The numerator, we've got a minus bj, which is just the conjugate of z conjugate. And the denominator, a squared plus b squared, that's just the magnitude squared, right? It's the magnitude, but without the square root. So we have something very similar. We've got z conjugate over over magnitude of z squared. And for the question, it says that we've got z. The numerator z, that's the only difference. But it says that this equation only holds true if and only if z is a real number. If z is a real number, then we don't have that the bj term, meaning that z conjugate equals z. So since we have this condition that z must be a real number, that makes this true. So this one's good. Let's do that in green. So next one. If z, the magnitude of z, is greater than 1, then the magnitude of z squared must be greater than z. This one is also pretty straightforward. So it's basically saying if a squared plus b squared, that's the magnitude, if that's greater than 1, then a squared plus b squared must also be greater than the square root of this number. And since it's greater than 1, we know that this is true because we're not working with fractions here. If we were working with fractions, then they might get smaller when we square them because the denominator would be squared and the numerator would just be 1. But since we have this condition that z is greater than 1, then we know that this one is also true. So next question. If any two arguments of z differ by k pi, where k is an integer, any two arguments of z differ by k pi, where k is an integer. So this one's a little bit confusing because we know that, let me do it off to the side here. If we have like an Argand diagram here, imaginary axis and the real axis. So if we were taking like the second roots of some complex number, and we have here like w naught, and then we had the other value here. If we were taking the second roots, then we see that it does differ by pi, right? It makes sense when we're talking about the second roots because they need to be equally spread out around that Argand diagram, or like for a 2 pi revolution. But since this question just says any two arguments of z differ by k pi, So it's just kind of confusing, and like we're not even talking about like complex roots here. So for that reason, it leads me to believe that this one must also be false. So false. And then E says none of the above are true, and we have B and C are true. So therefore, B and C are the only true ones of number 1. So let's hop into number 2. So question 2 says we've got x1, x2, and x3. That is a linearly dependent set in R3. So which of the following must be true? So before we even get into this, let's just remember, what does linearly dependent mean? So linearly dependent means that some of these vectors can be represented as the linear combination of the other vectors in the set. So question A says each of the vectors x1, x2, and x3 can be expressed as a linear combination of the other 2 vectors. So this one, basically, if we can think of like an example of a set where it's linearly dependent, except we actually can't come up with the linear combination of the other 2 vectors for one of the vectors, then we can show that this is false. And it's best to show this with an example. So let's say that we've got the vectors 1, 0, 0, 0, 1, 0, and then the 0 vector, right? So we can tell that this set is linearly dependent because 0, 0, 0 is the linear combination of 0 times both of the other vectors, right? 0, 1, 0. So we've just shown it's linearly dependent, but you cannot have a linear combination of this first vector here, 1, 0, 0. Like, there are no constants here that you can solve for that will make this hold true, right? So shown by a counterexample, we know that A is false. Okay. So to B, it says the span of x1 and x2 equals the span of x1 and x3, which equals the span of x2 and x2. So this one would be true, except we know that the span of x2 with itself is not true. If this said with like x3 and x2, that would be true. But since the span of x2 with itself, like geometrically, would be a whole dimension less than these, right? Because we can remove a vector, except with, oh, oops, didn't mean to do that. But with the span of x2 and x2, like that just property, like we've never seen that anywhere. So we just know that that's not true. So 2C, the volume of the parallelepiped determined by x1, x2, and x3 is 0. So since we know that this is a linearly dependent set, it means one of the vectors is a linear, at least one of the vectors is a linear combination of the other 2 vectors. So thinking of that geometrically, we know that, let me think of a way to draw this out. So geometrically, we know that since we're a linearly dependent set in R3, that means that we are either spanning a line or a plane, right? We're not spanning R3. If we're spanning R3, then that would be linearly independent for these 3 vectors. And we know that the volume, for us to have a volume, we need to be in all of 3D space. If we were on a plane, the volume would be 0 because we'd be squished. And then if we were all on a line, we'd also be like squished, so the volume would be 0. So just thinking of it visually, we know that the volume must be 0 because it's a linearly dependent set. So this one is true. So D, one of the vectors, x1, x2, and x3, is a scalar multiple of one of the other vectors. And we know that this is false because one of the vectors is a linear combination of the other two vectors. So for that reason, this is false. And the same goes for E, because we have 2C is the only correct answer. So moving to 3, we have U and W be some n-dimensional vectors that are not 0. So which of the following must be true? Okay, so this first one, let's just think of this with the formula for projection. So if we were to write this out, we've got projection of UW. So we've got U dot with W over magnitude of W squared all times W, and that's all dotted with W divided by magnitude W squared, and we need to see if this is equal to just the projection of U and W. So we've got this, and we also know that this here is a scalar, and this denominator here is a scalar. So we've got U dotted with W, and this will be W squared times W squared, and this is W dotted with W. We know that W dotted with W is equal to magnitude squared. So that means that one of the terms in the denominators cross out, and we have the same thing. We've got this projection up here. So we've got the left-hand side. We've shown that it's equal to the projection. Equals U dot with W over magnitude W squared times W. So 3A is true. Okay. That kind of took up a lot of space. Let me erase this. Okay, B. We have basically the perp of a perp on itself. Is that going to be equal to the first perp? Okay. Excuse me. So I think that let's think of this one geometrically, because that looks like it would be really messy if we tried doing it geometrically. So let's just take some U and some W. This is U. That'll be W. So the perp of U on W, first let's find that. We know that will be this green arrow here. And I'll just write it as perp. So if we were to take that perp onto W, we've got this green vector onto W. So let's remind ourselves, what is this perp? This, or like the left-hand side, the perp of the perp. So we know that it'll be the vector that we're taking the perp of, which in this case is the green one. So let's write that out. We've got the perp of U on W, and that's minus the projection of that same vector onto W. So the first one would be the perp of U on W onto W. So let's just think here. And we've kind of visualized this on this right-hand diagram. And the perp, or the projection of this green arrow, or like if we were to take the projection of the green arrow onto the red arrow, that would be 0, right? Because since it's perpendicular to it, so that would take this entire section to 0, which means that we'd just be left with the perp of U on W, and that's equal to the right-hand side. which means that B is also true. So question C, we've got the perp on the projection and then the perp on the projection again. Okay, solid. So let's just visualize this. We've got some u, we have some w. We know that this will be the perp, and then we've got this will be the projection. And the left-hand side is saying the perp of the projection on u on w. So let's think here. We've got what is the perpendicular component of the projection of u on w onto w? So it's basically asking us, if we've got this green vector, if we took the perp of it onto that red vector, which is w, then what would be the perpendicular component? And we can clearly see that since they're lying right on top of each other, then that will be 0. So then we can think the same thing of the right hand side. We've got what is the projection of the perp onto w? So we know that the perp is going to be the vertical component, and then we've got onto w, which is that red vector there. And we know that the projection onto itself, since it's perpendicular, similar to the last question, that would be just 0 as well. So we know C is also true. So question D, we have got the projection of u on w plus the projection of w on u is a scalar multiple of w plus u. So let's think here. We have u dotted with w over magnitude of w squared, and then plus we've got w dotted with u over magnitude of u squared in the u direction. So we can rewrite that as just c1 plus c2, or c1 times w plus c2 times u. And if we look at the right hand side, we've got a scalar multiple of w plus u. And a scalar multiple of w plus u would be something that looks like that, right? W plus u. So we can't necessarily say that this is true, because in the first case we've got each of these vectors scaled and then added together. But in the second case we're adding together the vectors first and then we're scaling it. So that's not necessarily true. So therefore, we've got A, B, and C as the only correct answers here. Alright, question 4. We have, we're given two vector equations of, just two vector equations, L1 and L2. And it's given basically all in terms of variables, and it asks us some questions. So which of the following is true? We have L1 passes through the origin if the vector OP1 equals the 0 vector. So this could be true, but since that origin to P1, that P1 is just a point on the plane. It can be any point on the plane. So if we had another vector that described as that origin to P1, then that doesn't say that the origin doesn't pass through, or L1 doesn't pass through the origin. We're just I guess like anchoring it with our vector equation at a different point. So we could choose, there could be some parameter t in this case that we add to that vector OP1 that would be equal to the 0 vector. So in that case it would still pass through the origin, and OP1 would not be equal to the 0 vector. So the first one is false. For B, there is a plane in R3 that contains both of the lines. So this one, if you just kind of spatially think about this in R3, we know that this would be false, because if the lines were not parallel, or if they were skewed to each other, then there's no way that we could get a plane that contains both of those points. And this you can kind of just think of visually and know that it would be false. So for C, we have if L1 and L2 are parallel, and A is a point on L1 and B is a point on L2, then the shortest distance is given by this thing. So let's just sketch this out. We've got, okay, this is L1, this can be L2, and it says that A is on L1, so we'll just choose an arbitrary point, A. This can be B. And then D1 is the direction vector of L1, meaning, so it's this one right here. So this is D1. And it's saying that we know that the shortest distance, so let's try to graph what they are telling us, perp of AB onto D1. So AB is this vector in blue onto D1. That means that this vector here that I just highlighted, that is the perp. And since that's the perpendicular distance between those two parallel lines, and we're taking the magnitude of it, we know that that is true. This is the shortest distance. Therefore, C is correct. Okay, and then for D, we've got the equation x is OP plus t times the direction vector of the first line plus another parameter times the direction vector of the second line. This will be the vector equation of a plane through point P. So it looks pretty true by looking at it, but we just have to realize that there's other cases. For example, if the direction vectors are parallel, then that would result in just the equation of another line, right? If D1 and D2 were different directions, this would be true, but we don't know that since we're not told in the question, it's not specific enough. So for that reason, this one is false, meaning that 4C is the only correct answer here. Okay, so number 5, what is the shortest distance between these two planes? Okay, solid. So let's call this plane T. The first one is T, and then we'll do the second one is D. Just want to give them random variables. And you can tell that these planes are parallel since their normals are scalar multiples of each other, right? We've got 1, 2, 1 is the normal of T, and 2, 4, 2 is the normal of D. So we know that they're parallel. So let's just draw an arbitrary point on, let's say this is T, let's say this one's D, and this is point D. So if I were to draw a vector that connects these two lines, this would be point D to point T. And then we've got the normal of D. So we need to find the magnitude of the projection of those 2 points onto the normal. So we've got projection, or magnitude of projection of point D to point T onto the normal of D. Okay, so now we need to figure out 2 points on both of these planes. So just by inspection, by plugging in values x1 and x2 and x3, we can just make sure that it is equal to the right hand side. So a point on T could be 0, 1, 0. A point on D could be 1, 1 half. So point D to point T, and I'm sure you guys know how to do this at this point. We just subtract, so we would get 1, 0, half. And sorry, this should say point T to point D. T to D. And then we've got the normal. So basically, we've got the normal of D is equal to 242. Okay. So then, taking the magnitude of this, we've got absolute value of the dot product of these guys. So we've got 2 plus 0 plus 1. And then divided by, we've got 2 squared plus 4 squared plus 2 squared times, this is magnitude of the normal, 4 squared plus 2 squared. This will be equal to 3 over, so we've got 4 plus 16, which is 3 over 24. This will be square root of 24. This will be 1/8. And we can express 24 as 6 times 4. Square root of 4 is 2. We've got 2 root 6, or root 6 over 4. And we can see that that is option D, meaning that 5D is the correct response. Okay. So question 6. Which of the following must be true for, basically defines A and B to be some subsets of Rn, and it gives us M as the intersection of A and B and N as the union of A and B. And this one definitely looks pretty confusing to start out with. So what I like doing for these kinds of questions is visualizing it with like a Venn diagram. So if I had this space, and this space, this entire box is Rn, and I've got A and B, so we'll represent that as 2 circles, like a Venn diagram. This is A, this is B. So this section that connects both of them right here, that would be A intersection of B. And then this entire green area here, that would be the union of B, A and B. So we know that's equal to N. The other one, the intersection, is equal to M. So 6A, M and N are both subsets of Rn. And we can basically know that since the green area and that red area, since they're both inside of that box, then they must be subsets of Rn as well. So this one is true. Okay. M is a subset of A, and A is a subset of N. So let's look at this. We've got it's asking us, this red area, is this a subset of A? So let me draw this again, a little bit more clear. So this is A, this is B. So is M a subset of A? We know that A is this entire circle here that I just highlighted, and M is the intersection of A and B, which is this green area here. And since that green area is inside of that highlighted area, we know that M is a subset of A. So now we need to show that, or we need to see if A is a subset of N. And we know that N is the union of A and B, which is this entire green area. So since all of that highlighted area is inside of that shaded green area, then we know that A is also a subset of N. So B is also true. So now it gets a little bit more confusing because it starts redefining things. It says if, let's say that the intersection of A and B is equal to A, then A is a subset of B. So let's see. So let's just think of what that would mean in terms of this Venn diagram. If we're talking about the intersection, and it says that the intersection is equal to A, then that means that the circles, they kind of have to lie on top of each other, because the intersection must be equal to the circle itself. So if M is equal to A, which is what we have here, then A is a subset of B, and A basically lies right on top of B, so we know that A is a subset of B. So this is true. Okay, so then we've got if N is equal to A, then B is a subset of A. So let's think about this. It's saying if the intersection of A and B is equal to A, then B is a subset of A. Or sorry, if N, since N is the union, pardon me. So we've got, let's draw this big circle A, and we know that the union, they don't have to necessarily lie right over top of each other since it's the union, but we know that A has to basically like engulf B, because we're taking all of it. So if B was bigger than, if we had both of them, then you see how now we're kind of like leaking out of A, and we know that that's not true. It tells us that it is that the union has to be equal to A. So B could be somewhere like inside of here. So the union is all of the area of both of them, right? It's A or B. So then B is a subset of A. And we know clearly from the diagram, since B is like directly inside of A, then D must also be true. So lastly, we've got if M is equal to N, then A is equal to B. So this one is saying if the intersection is equal to the union, then A must be equal to B. So similar to one of the previous cases, if the intersection and the union are the same, then the circles are lying like right over top of each other. And clearly you can see that A and B must be the same in this case. So 6E is also true. So in this case, every single one of these is true. But yeah, that's it. I hope this was helpful.